Unlike the first semester, where each of the chapters were kind of disconnected samplings or pieces of stuff, this is going to be a continuous build-up throughout the course.
Okay.
And the solution phase was kind of a warm-up, but we're going to start with reactions. We're going to get into equilibrium. We're going to get into acid-base. And each chapter is going to build on the stuff from the previous chapter. So let's start by understanding the rates of reaction and going from there. Now, if we're talking about the rates of reaction, we're talking about a sub-discipline of chemistry called kinetics. Kinetics are basically how fast the reaction is going to go. Let's see, we're going to dive into what kinetics are, how we measure the rates of reaction. We're going to talk about things like relative rates and average rates, and then we're going to get into talking about how we can measure rates, and then how to predict rates. And that's about what we'll cover for this first meeting. And then in the second meeting, we'll get into some subsequent rate laws. And next week, we'll go into some more details about what those rate laws mean about the individual reactions. But just to start with, the basic concept of kinetics is how fast does it go? This is not stoichiometry, although stoichiometry will play a role here. We're not asking anymore about what's going to form or how much is going to form. What we're talking about here, what we're exploring, is how fast it's going to form. And that's an important facet to chemical reactions. I mean, if you think about it, like an ocean liner. Does an ocean liner dissolve in water? What do you think?
An ocean liner?
Yeah, you know, sodium chloride dissolves in water. Does a ship dissolve in water?
No.
Actually, it does. So here's the thing. Battleships and ocean liners, they don't last forever. They dissolve in water. But the key is the chemical reaction that causes them to dissolve in water takes decades. So that battleship can last you 40, 50, 60 years before it dissolves in water. So how fast the chemical reaction can have a huge effect on the utility of that ship. And if you can slow it down, you can get an extra decade of use out of that ship. And if you speed it up, you can cause real problems for a ship. Things like sugar. Sugar isn't stable. We burn sugar in our bodies. That's how we get energy. And how fast we burn the sugar means how much energy we have available to us. The speed of that reaction by which we chew up the sugar, adjusting the speed of that reaction really affects the utility of it. Propane, you know, how much energy you get out of fossil fuels, propane, it's also a function of how fast you get energy out. I mean, propane and acetylene, you can get out you can get out energy in different ways. But how fast it takes for that battleship to dissolve, how quickly you can metabolize sugar, how fast you can burn a fuel, all of these things have implications on the reaction beyond just what the products are. And this is kinetics, and this is understanding the rates of reaction. This is what we're going to get into. Now, when we talk about the rates of reaction, we talk about, you know, how fast the reaction occurs. Well, we're scientists, we're chemists, we want to have numbers to it. So we're going to need a way of getting a handle on how fast the reaction occurs, which means we need something to observe. What we're frequently going to do is we're going to observe concentration. If I have a flask with some ink in it, how fast that ink decomposes, we can observe it by the change in color in that flask, because that's directly relative to the concentration. At the start, the thing that's dissolving is very concentrated, and as we go forward, the concentration is going to change. And so how quickly the concentration changes, how quickly it goes from a dark violet solution to a clear solution, how many minutes it takes, or how many days, or how many weeks or years it takes. That's a measure of how fast the reaction's going. We just finished a chapter where we looked at solutions. We looked at different measures of concentration. One of those measures we're going to use a lot in here is molarity. Shortcut for describing the molarity of a substance. Like, for example, in this reaction, when I'm talking about the molarity of A, I'll just put A in square brackets. And what I mean by that is the concentration measured in molarity of A. If I say A, I mean the substance. If I mean A in square brackets, I'm talking about the concentration of that. And as this reaction goes forward, well, A is going to be chewed up. Now, here's the interesting thing, is you're watching this reaction go forward. As you're watching A go forward, you're going to see this concentration change over time. And we can describe the rate of reaction, or how fast this reaction is going. Actually, let me rephrase that. We can see the rate of change of A, how fast A is changing, by looking at that change in concentration, that delta of concentration. Remember last semester we talked about delta and what delta means? What does a delta mean? That if I put a delta in front of T or a delta in front of H, what's the literal meaning of that delta symbol?
The change in something, whether it be temperature or the kilojoules, any of that stuff.
You're absolutely right. And there is a difference between the measure of something and a delta of something, or a change in it. And that delta, whether we're talking about temperature or energy, we always mean final state minus initial state. We talk about the change from the point of view of time going forward. And so we always say final minus initial. And what a rate is a change in something over a change in something else. And what we're going to most often look at rates are a change in, well, material amount, concentration over a change in time, a delta in time. So T final minus T initial of my concentration over T final minus T initial, say, of time. Now, in this reaction that's in front of me here, if I look at the first 100 seconds of this, what's the delta of A?
It's the 0.100. Is that what you're looking at?
So yeah, so what they're telling me is the initial concentration at time 0 is 0.100, and at 50 seconds it's 0.78, and at 100 seconds it's 0.059, and at 150 it's 0.043. Over the first 100 seconds, what's the delta of the concentration of A? And as a hint, delta is always final minus initial. So look at the last one, subtract the first one from it. What's the delta of A? There's a trick to
it. 0.041. It's a negative.
That's the trick. You're right. You're absolutely right. It's 0.041, and it's a negative, okay? So the delta here is 0.041 negative. And if I wanted to know the rate of this, the rate of the change of A, what would the rate, then I would take a look at the final minus initial of the time, and I would divide that delta of A over the delta of time. What's the rate of change for A in this reaction? Delta A over delta T is what number?
I'm kind of lost there. So the change in A, delta A, would you take everything listed on the chart, or would you only go by a certain portion of the chart?
It's a darn good question. In this particular question, they're asking about the change in A, and actually they're being specific. They're talking about the rate of disappearance, which already has that negative rolled into it. So they're asking for the rate of disappearance of A. And this is a question you may run into in the homework. What is the rate of appearance of B, or what is the rate of disappearance of A? And the way you do that is you find the delta of A or the delta of B and divide it by the corresponding delta in time. So in this case, I'm going to take that 0.041 you found, and I'm going to divide it by the delta of time. And the delta of time in this case is, well, 100 minus 0, so 100. So if I take that 0.041 and I divide it by 100, then looks like the answer here is C. Do you see how I came up with the rate of change of A?
Yeah, I did. I guess what's confusing me, because on the homework, even I would, well, like in this case, you only went up to 100. How would you know if you need to use the entire chart? That's confusing to me.
I'll give you a preview. In a couple slides, I'm going to point out that the number, the rate of change between 0 and 100 is different than the rate of change between 100 and 200. So how do you know which one to use? Depends on the question you're trying to answer. So if they're asking you what the rate of change, in this case, in the first 100 seconds, that shows you where on the chart you got to go. But you're right. One of the things we're going to find is as the reaction proceeds, the rate of change of any of these substituents can increase or decrease as the reaction goes forward. In this case, we're just trying to lock down what we mean by a rate of change. And a rate of change is just one delta over another. And we'll almost always be talking about, when we're talking about rates, the delta in the bottom is going to be delta time. So, but you're right, the window of time that we're looking at is important. And that's a difference between instantaneous rates and average rates. And yeah, there's a lot of rates that are going on in this reaction. In fact, let's talk about a couple different kinds of rates that are going on in the reaction in terms of, for example, relative rates. This is, if I have this reaction, I might observe by looking at how the concentration changes, and I might find the rate of change of A is negative 4.1 times 10 to the minus fourth molarity per second. Let's just make it simple. Let's say that the rate of change was equal to negative 2 molarity per second for A. Now here's the thing. The rate of change of A is not going to be the same as the rate of change of B or the rate of change of C. But they're all linked to each other by stoichiometry. So if you know the rate of change of A for a given interval, you're going to know the rate of change of B and C. If the rate of change of A is, say, minus 2 molarity per second, what's the rate of change of B?
It's going to be 2 times 2 of the value of A, correct?
Yeah, totally. Because with every tick of the clock, you consume an A, but you consume 2 Bs. So whatever the rate of change of A is, whatever the rate of change of B is, it's going to be twice the rate of change of A. And if the rate of change of A, a reactant, which is going to be negative, then the rate of change of B is going to be, well, twice that. The coefficient links the two. How about the rate of change of C? If the rate of change of A is negative 2 molarity per second, what's the rate of change of C? It's similar to how we found B, but there's a twist.
To find C, you would have to get the value for B first, correct?
Well, I could, as long as I know the rate of any one of these, I can go directly to the rate of any other of these. So I could go from A to C, or I could go from B to C, or I could go from C to A. But once I know one of these rates, and I'll tell you in advance, the only way you can find these one of these rates practically, effectively, is by an experiment. But once you find one of the rates by experiment, they're all linked, and therefore, by theory, you can discover the rate of every other piece in that reaction. So the first thing to realize is that the coefficients scale the rates. In other words, the simple fact that every time I consume an A, I consume two Bs means the rate of change of B is going to be twice the change of A. Now, there is a trick here. The coefficient in front of C is 3. What's the coefficient in front of A? There's a trick to it.
Nothing, so it would be 1.
So if we don't see a coefficient, we assume that it's unity, but here's a trick. The stuff that's on the left side of the arrow is being consumed. So yeah, if someone asked me what the coefficient of A is, I'd say 1. It's a reactant with a coefficient of 1, which means it's being consumed, which means, well, effectively, that coefficient is a -1 because it's on the left side of the arrow. And the coefficient in front of B, if someone asked me on a test, I'd say the coefficient is 2. But when I'm working with these things, when I see that 2, I think of it as a -2. And on the other hand, the coefficient in front of C is a +3. So the relationship between A and C is not just 3 to 1, it's 3 to -1. So if the rate of change of A is -2 molarity per second, what's the rate of change of C?
It would be 6.
Yeah, +6, right?
Yeah, yeah.
Words, A is being burnt up, B is being burnt up at twice the rate of A, and C is being produced, in other words, flip the sign, at 3 times the rate of A. So when you're talking about relative rates, the signs matter. But once you know any one of those rates, you can find all of them by stoichiometry. So like I say, here's another reaction, hydrogen and iodide. Hydrogen and iodide react to form 2 HIs. The rate of hydrogen and the rate of HI are different, but they are linked, they are related. If I know what the rate of hydrogen is, the rate of iodide is going to be the same, and both those rates will be negative, and the rate of hydrogen iodide is going to be twice that, but positive. So in other words, the coefficients in front of those things link the different rates. Now, do you remember when we were talking about thermochemistry, we developed a heat of reaction?
Yeah.
Is the heat of reaction for hydrogen, for iodide, or for HI? It's totally a trick question. I'm trying to mess with you here. It's none of the above, right? The heat of reaction is something that's not specific to hydrogen. It's not specific to iodide. It's not specific to hydrogen iodide. The heat of reaction is something overall about that change. It's about the difference in energy between the sums of hydrogen iodide and hydrogen iodide. The heat of the reaction is not about one component. It's about how the components relate to each other. Okay. Similarly, we're going to develop something called the rate of reaction that, like heat of reaction, is not about hydrogen or iodide or HI, but is related to all 3 of those. The rate of reaction is an independent number that describes the overall change. And it's linked to all these individual changes, which are all linked to each other. Now, in a laboratory, the way you're going to determine the rate is you're going to observe one of these things. You're going to look at the change in concentration of hydrogen or iodide or HI, and you will measure the rate of change of, say, HI. And you want to, but you don't want to record that in your lab book because the guy who comes after you might not care about the HI. He cares about how fast the hydrogen is being consumed. And maybe the lady after that is going to be concerned about how fast the iodide is being consumed. You want something that steps above any of the participants and talks about the overall reaction. That's the rate of reaction. And it's not the rate of change of H or rate of change of I or rate of change of HI, although those are important. The rate of reaction is derived from any one of those. The rate of reaction is defined by taking any one of those rates and dividing it by the coefficient that's in front of it. So for example, in this particular reaction, if somebody gave me the rate of reaction of HI, I would take that number and divide it by +2, and that would give me the rate of reaction. And if somebody asked me, say on a test, what's the rate of reaction, and they gave me the rate of HI, I would take that rate and divide it by +2. Now, if they gave me the rate of hydrogen being consumed, they told me the rate of hydrogen is -2 molar per second. What would I do to that to get this overall number, this rate of reaction? Would divide it by the coefficient, right?
Yeah, that's what I mean. I'm kind of lost on all this stuff. Yeah.
Okay, but here's the trick. What's the coefficient in front of H, which is a reactant?
It would be a -1.
You got it. That's the trick. So if anyone ever asks you, what's the coefficient in front of H, say 1. But since it's the reactant, when you're using those coefficients, especially with kinetics, think of it as a -1. So to get the rate of reaction, you would take whatever rate they gave you for H2, maybe it's 2.0 molarity per second, you would divide it by -1, and so the rate of reaction would be +2.0 molarity per second. And the rate of HI, which is twice that, would be +4 molarity per second. You want to see another example of this so we can kind of work through those relationships a little more?
Yeah.
Let me give you a real example. Do you know what hydrogen peroxide is?
I've used it before, yeah.
Hydrogen peroxide is a really useful substance. First of all, it's the only peroxide I know that's not explosive. So you can keep this one in your medicine cabinet. Most peroxides you don't want in your home, but hydrogen peroxide it won't blow up on you. It's not stable. If you leave it uncapped, it's going to decompose. It's going to break down the water in O2. So if you leave a bottle of this on your counter, it'll turn into water eventually. But it's really useful. If you get a little bit of blood on a white shirt or something like that, pour the hydrogen peroxide on it. Don't put it in the hot water. Just pour the hydrogen peroxide on it. Let it sit for about 5 minutes, and the blood will turn brown, and then it'll rinse out in cold water. Anyway, hydrogen peroxide is useful stuff. Now, let's say you got a bottle in your medicine cabinet, and we left it uncapped. So it's starting to decompose. It's starting to break down. And we want to find out how fast it's breaking down. I can put an oxygen meter next to it, and I can determine that the rate of change of oxygen in this reaction is plus 0.0014 molarity per second. Okay, so if that's the rate of change of the oxygen, what's the rate of change of the peroxide? How is the peroxide changing? And there's a couple numbers to pick from here. What do you think?
First of all, it would be a negative then, correct?
Yes.
Because the oxygen is positive?
Right. The oxygen is being produced, but the peroxide's going away. It's breaking down on me.
So you would take the 0.0014 and times it by 2. So it would be 0.0028, but it would be negative. So G?
Totally. You nailed it. Yes. All right. How about the water? The water and the peroxide both have a 2 in front of them. Is the rate of change of both of those the same? I'm messing with you. I'm totally trying to trick you.
The screen is changed.
Oh, okay. Sorry about that. I was trying to set up the next slide, and it hit my monitor. Okay, go for it. So so you've identified the rate of change of peroxide as G, negative 0.02A. What's the change of water?
It would be positive 0.0028.
Yes, it is. You're right. So all three of those things are changing at different rates. The peroxide's changing at negative 0.0028. The water's changing at positive. The water's actually being produced positive 0.0028. And the oxygen, like we said, is being produced at 0.0014. So there's different rates on all of these things. Now, here's the thing. If you want to record this information in a book, you could record any one of those changes. You would have to measure one of those things because you can't measure rate of reaction directly. You have to measure the change of something physical, like the peroxide or the water or the O2. But what we're going to try and capture, the way we're going to characterize this chemical change, just like we used heat of reaction when we're talking about thermochemistry, we're going to use rate of reaction when we talk about how fast it's going. So here's the million-dollar question. What is the rate of reaction for this reaction?
So you would take the oxygen and for the positive and the positive H2O, add it together and subtract the 0.0028 for the H2O2. Is that correct? Or
so the trick with this is, if we want the rate of reaction, all we have to do is take the rate of any one of those, the peroxide or the water or the hydrogen, the oxygen, the water, or the peroxide, and divide it by the coefficient. Any one of those will give us the rate of reaction. We just have to divide it by the coefficient, remembering that reactants have a negative coefficient and products have a positive coefficient. So, for example, I could take the peroxide, which you told me is negative 0.028, and divide it by a negative 2, and I would get positive 0.014. I could also take the water, which you told me the rate of reaction is positive 0.0028, and divide it by positive 2, and I'll get the same number, positive 0.014. In this case, the oxygen's got a 1 in front of it, and that 1's positive, so the rate of oxygen, all I got to do is divide that by positive 1. In other words, it's the same number. The rate of reaction is 0.014 molarity per second, positive number. So it really doesn't matter which one I start with. With any one of those, I can get the other two. And with any one of those, I can get the overall rate of reaction. Does that make sense?
yeah, it does. And when you say divided by the coefficient, like on the last slide that you had, it has the negative 1 over A. The A would be the coefficient then, correct?
That's correct. You see how
Okay.
at the bottom there, I say little a, capital A, plus little b, big B. That's
Right.
kind of a shortcut for saying I got something called A and its coefficient is something called little a.
Okay.
So in the reaction above, the A is hydrogen and the coefficient's, well, negative 1. And the iodide is the B and the coefficient there is also negative 1. The hydrogen iodide is the C and its coefficient is positive 2. And if anyone ever asks you, what's the coefficient in front of I1, don't say negative 1, you'll confuse them. But when you're working with kinetics, or for that matter, when you're working with stoichiometry, when you're looking at these coefficients, it's useful to see the coefficients in front of the reactants as negative numbers and the coefficients in front of the products as positive numbers, because that really is what they represent. With each tick of the clock, 2 HIs are appearing, positive number, but 1 H is disappearing, negative number. The stuff on the left of the arrow is being consumed, the stuff on the right of the arrow is being produced. Right. Anyway, this is rate of reaction. And like I said, it's not the same as rate of change of H or I or HI, although it is equivalent to the rate of change sometimes, like in this reaction, where the numeric value is the same as, well, the rate of change of O2, because the coefficient in front of O2 is 1. But the rate of reaction is a separate number. There are 4 rates here. Just 2 of them happen to be equal to each other. But there are 4 rates: the rate of peroxide, rate of water, rate of O2, and then the rate of reaction. That is the overall rate for that, that chemical change. This making sense?
Yeah, it does.
Nice. Okay. All right. So relative rates is starting point. By the way, This class is going to stick with you for a long time. If you decide you want to go to medical school, you're going to take the MCAT. They're going to test you on the stuff from this class. If you decide you want to get a job in a hospital or you want to get a job in a forensic lab, they're going to say, hey, your first day, why don't we figure out where to put you? Here's a placement test. The questions you're going to see on those placement tests, those standardized tests, many of those questions are going to be about content in this class, because this class is such a pivotal point in your collegiate career. And they will frequently ask questions from the beginning of the second semester of general chemistry to see if you started the second semester of general chemistry. And those relative rates, man, they love those on standardized tests. Those show up a lot.